can use softmax here if you want. Okay. So, this has several things which are repeated even now in current networks. One is that as you go deeper into the network, starting from the input, the size of the feature maps typically shrink because of the convolutions, also by the pooling operation, which is actually a subsampling operation. And not only that, as the size of the feature maps it decrease, the number of feature maps increases. So, in the end we have 120 1 cross 1 feature maps. Among the first layer we have about 6 feature maps of size 28 by 28. So, this general principle is, you will see, is reflected in in the current architectures also. So, this network achieved state of the art results in 1998 for digit recognition based on the MNIST digit database. In this video we will look at AlexNet, which was this work was done in 2012. So, AlexNet was the entry to the ImageNet large scale image recognition challenge, and this was among the first CNNs to be entered into the challenge. And it actually beat all its nearest competitor by more than 10 percentage points. Okay. So, this was a deep neural network with about 7 layers, okay, and 60 million parameters. Okay. So, this was the structure of this network is, the architecture of the network is very similar in terms of very similar to LeNet-5 in terms of the convolution and max pooling operations, but then it had various other innovations in it, as we will see in this video. So, just to give a brief overview of this network. So, the ImageNet challenge, the input, these are RGB images. So, the input layer at size 220 24 cross 24 cross 3. Some sources have pointed out that it should be actually 227. Cross 227 in order for the output in the second layer to be consistent. Okay. So, the in order for the output in the second layer to be consistent. Okay. So, the first convolution layer had a 11 cross 11 filter, 11 cross 11 filter with a stride of 4, giving rise to 96 feature maps of size 55 by 55, and then we have a this work was done in 2012. So, AlexNet was the entry to the ImageNet large scale image. This was a network, is the architecture of the network is very the ImageNet challenge, the input, these are RGB images. So, the input layer at size 224 cross 24 cross 3, some sources have pointed out that it should be actually 227 cross 227 in order for the output in the second layer to be consistent. Okay. So, the first convolution layer had a 11 cross 11 filter, 11 cross 11 filter with a stride of 4, giving rise to 96 feature maps of size 55 by 55, and then we have a max pooling operation here, max pooling operation using a 3 cross 3 kernel and a stride of 2. So, which leads to effectively halving the size of your feature maps. and stride of 2, so which leads to effectively operation using a 3 cross 3 kernel, and stride of 2, which leads to effectively halving the size of your feature maps. again again followed by full. So, the stride of 1. Okay. So, the layers you see here in this case. So, I earlier mentioned that 5 cross 5 for almost all of the convolution operations, but in these intermediate layers the filter kernel size was 3 cross 3 for all these 3. Okay. And they had a padding 1. So, in these boxes the intermediate convolution layers that I shown here has where convolution filter kernels of size 3 cross 3 with a pad of 1 to preserve the size of the feature maps, followed by a max pooling and then a fully connected layers, 2 fully connected layers and an output which is 1 of 1000. So, the ImageNet classification challenge provides you 1000 image categories and you have to classify them as 1 of 1000. So, a pretty deep network at about 7 layers. So, if you count, it is about 1, 2, about 5 convolution layers, about 3 max pooling. Okay. Typically about 7 layers, which included convolution as well as the densely connected layer. So, if you just count the convolution plus the fully connected layers, you will have about 7 of them. This network also had a normalization layer normalization, where it is called local contrast normalization. This was done by, if you look at a particular pixel or an activation in a feature map, you normalize its value by looking at the adjacent feature maps at the corresponding feature location. So, this was, but of course, this is no longer done. This was the one off thing that was done for this particular realization of the network. So, another thing that this network again had, if you look at this network, a lot of the computations happen in the earlier layers, because you have 11 cross 11 convolutions, 5 cross 5 and 3 cross 3 convolutions. Okay. But if you look at the fully connected layers, in the end, lots of parameters here. Most of the parameters come from here, because you see if you look at these two fully connected layers, this is like 4096 times 4096 weights. Okay. And if you look at the max pooling following this is for 2. .256 cross 13 cross 13 as input to the max pooling layer with the stride of 2. So, you will have about 256 cross, in this case, if you have pooling 3 by 3, you have 2 cross 5 cross 5, I think, and you unroll this and follow up with a fully connected layer to a 4096 activations. Okay. So, a lot of the parameters occur towards the end, and a lot of the computations are at the input side of the layer of the network, because of the size of the convolution kernels. So, if you see, this network actually has a mix of 11 cross 11, 5 cross 5 and 3 cross 3 convolution kernels. So, let us just look at this convolution layer at the input. So, this one aspect of this network, which is now highlighted in this figure, is that the GPUs available at that time, the one this particular network was trained, had only 3 gigabytes of input of memory available. So, the computations for this network were split across 2 GPUs. So, if you look, we have split the network from the previous slide into 2 pathways. So, basically the top here, all the computation in the top of here would go to one GPU, and all the computation at the bottom of here will go to another GPU. Okay. So, for the first layer we have 96 filter kernels as we saw. So, 48 of them in one and 48 of them in the other. Okay. So, if you look at the number of parameters here, it is very easy just to show an illustration of how to calculate the number of parameters. Let us say on just one pathway we have, each filter has (11 cross 11) parameters. Okay. So, we have about 48 of them in one. Okay. And there are 2 pathways, in this case GPU 1 again and GPU 2. So, it will about times 2 parameters per convolution layer in one convolution layer. Okay. And it produces 96 of course feature maps. So, we have to that is why we have 48 times 2, 96 feature maps. Okay. So, the size of the feature maps is 55 by 55. So, these are number of parameters. So, if you want to calculate the number of computations that you have to do per GPU, for let us say number of computations per GPU. So, you have the output size is 55 cross 55 times 48. So, those are the total number of activations in the on one GPU in this particular computational layer, convolutional layer, and for each of these we have to calculate the this is the number of for each one, to produce each output we have to do 11 cross 11 cross 3 computations. Right. So, this is the number of outputs activations So basically 55 cross 48, and for each output we need to perform 11 cross 3 multiplications. I have ignored the additions that we have to do because it's the sum of products. You can put in a factor there for it if you want to, but this is the typical way to calculate the number of computations. Of course, the network is spread across 2 GPUs, so this is for one half of computations. Layer, again as I showed before in the earlier, so it's the weight matrix for a fully connected layer, which is very simple. That's how you would calculate for a regular artificial neural network. Of course, the number of parameters coming from the pooling layer to this layer is again much higher, because after the pooling you would have to unroll it and then to make it into a fully connected layer. Okay, so this is the typical computations required. So a lot of the number of parameters here are huge. This is the number of parameters that I calculated. Okay, but a lot of the computations happen in the earlier stage also. Okay, so there is another innovation here. As I referred, I said that as 2 pathways. That's because if you look at how the training was spread across 2 GPUs, you will see that except for in the layers where I have the cross arrows, these are the layers where I have cross arrows. In all the other layers, the ones here and here, the computations are restricted to the feature maps in that GPU. So this has, so let us say if you look at this particular layer, this has 48 feature maps, and we do a 3 by 3 pooling, but the pooling operation only draws from these feature maps. And when you do the subsequent convolution with the 5 by 5 kernel, then the 5 by 5 kernel actually acts across only these feature maps. That is why we call it the multiple pathways or 2 pathways, because, and if you come here in this layer, then the output activation here also has feature maps, includes feature maps from both the GPUs. Okay. So this one layer we have computations are involve both the or from feature maps in both the GPUs, while in the other layers they are done independently. So this is like having a separate pathway, 2 different pathways in the network. Okay, and this is one of the networks, the first time use of ReLU. We saw that in the earlier slide, ReLU, nonlinearity. It also used dropout regularization, we saw that earlier, dropout regularization. It also had data augmentation. So the data was, the images were augmented by, because you see the number of parameters is huge. There were a few million training images, but we have 60 million parameters, we do need more data if you have so many weights. It also used L2 regularization, okay, so that it does not overfit, to prevent overfitting to some extent. So dropout and L2 as regularizers. See, the data augmentation was done by flipping shifts, translations, as well as jittering the RGB values. So they are done dynamically on the fly as the network was training. Okay. So the network was placed first in the ImageNet recognition challenge, especially in the top 5 and the top 1 category. It had an error of about 15%, which was much higher than the second place finisher. Again, one of the earliest and the first CNN to win the ImageNet competition. So this network sparked a huge interest in deep learning, because it had lots of parameters. It was quite deep, 7 layers, and if you include the max pooling also, 7 weight layers, if you can call it that, because it had 1, 2, 3, 4, 5, 6 and 7 weight layers speak of, and of course interspersed with 3 max pooling layers. Okay. And it had a mix of filter kernels, 11 cross 11, 5 cross 5, 3 cross 3 kind of systematic. And if you also look at how the number of features increased as we go deeper into the network. So, the initial layers we had, first layer we had 96 and then 256 here, because I am adding from both of the GPUs, 384, 384, 384 was preserved. Okay. So, as you go deeper into the network, the number of feature maps increased, the size of feature maps shrank, but the number of representations increased. Okay. So, this is a typical architectural design that most networks use even now. Okay. So, you would, as you by the computational, basically the fully defined networks. Okay. So, that lead to also an improvement about 2 or 3 percentage points. So, multiple, and the layer normalization was also introduced here, but this particular layer normalization here is no longer used, but they do have a normalization layer in between the convolutional layers, just before the input of the convolutional layer. We will look at the VGG network, specifically the VGG 16. So, VGG stands for the Visual Geometry Group at Oxford University. So, this particular network was entered into the 2014 ImageNet challenge. Okay. So, it had 16 weight layers. Okay. 16 layers weight, this one we are looking at 16 weight layers. They also had another version which 19, VGG 19, had 19 weight layers. So, the design of this is very similar to LeNet and AlexNet, okay, except that they have made this a little bit more systematic. So, we will see what the systematicity is here. So, we saw one of the, in the earlier videos we saw that it's best that as we go deeper into the network, we increase the size of the depth, or the number of feature maps increases. So, it becomes wider, network becomes wider. Okay. So, that was incorporated here. They also stuck to one filter size. Size 3 cross 3, this is the smallest filter size, smallest meaningful filter size. So, 3 cross 3 gives you, you can also do 1 cross 1 correlation, but of course, we need a receptive field. So, 3 cross 3 is the small, they stuck to 3 cross 3 filtered throughout all the layers. There are a lot of parameters, about 130 to 140 million parameters, depending on which network you are looking at. Once again we will just walk through the network briefly, and then we will see what are the advantages given by this network. So, if you see the input again same, three channel RGB image size 224 cross 224. So, the first layer has two 3 cross 3 convolutions in succession, followed by a max pooling layer which reduces the size of the feature maps to 1 cross 2. And 12 cross 112, and each of these 3 cross 3 convolution layers had 64 feature maps, followed by another set of convolutions and max pooling, so on and so forth, till we get to the to these two layers which have again 3 cross 3 convolution, but this time 3 in succession, 3 of them in succession if you see here, followed by again a max pooling, and here of course these are rasterized and made into a fully connected layers here, these two, and the output is a 1 of 10, 1 of 1000 classification. Now this as if you look at this, we will see that this is a block. Okay, this is one of the earliest networks to introduce this kind of concept. We will see another network where most networks now use this. So, this is a block of convolutions. So, basically instead of your layer is now being replaced by a bunch of convolution layers. Okay, a sequence of layers is now used as one layer. So, in between these two convolution layers there is no max pooling, but the non-linearity is still there. So, 3 cross 3 non-linearity and then a 3 cross 3 non-linearity, okay, that is the sequence. Again in this case 3 successive non-linearities of are applied following the convolutions. So, what does this provide in terms of an advantage? So, if you look at a succession of 3 by 3 convolutions, one is the non-linearity leads to greater discrimination. Okay. Seeing that we have looked at other classifiers. So, if we have very non-linear features, we expect that at some point the classes become linearly separable. That is, but then how do we incorporate this here? Incorporate this here in the network is to have a succession of non-linearities, hopefully giving rise to better discriminatory power in the network. The second advantage is in terms of the receptive field. Okay. So, the authors also mentioned this, that if you look at this particular or we can just come here and look at this. So, for instance, if you look at these two 3 cross 3 convolutions, okay, so this is one convolution layer with 64 feature maps, 3 cross 3 convolutions, again 64 3 cross 3 followed by another set of 64 3 cross 3 convolutions. Okay. Now, if you look at the receptive field of this layer of this block, so the first one has a receptive field of 3 cross 3. Okay. So, that gives rise to 64 feature maps, right. So, now if you look at the second, if you look at the this is the first one, if you look at the second one, okay, the filter kernel size is 3 cross 3, okay, but the receptive field on the original image. So, we are looking at the receptive field of this particular layer on the input side. Okay. So, the receptive field for this one is 3 cross 3 and for the second it becomes 5 cross 5. It is not too hard to see because if you look at the second convolution, the feature maps in the second convolution layer, okay, we have a 3 cross 3. Okay. So, if you look at this particular activation in the feature map, then it itself is a result of a 3 cross 3 convolution. So, this itself is a result of a 3 cross 3 convolution, right. So, you have 1 2 and a 3 here, right. So, this particular feature map in the second 3 cross 3 convolution layer itself is the output of a 3 cross 3 convolution from the previous layer. So, this is looking at 3 1 2 let us say. So, then we see that all around we will have to add one more row and column. Okay. So, its receptive field on the input is actually 5 cross 5. So, similarly, if you look at the succession of 3 convolution layers, so the third the final receptive field for this the receptive field of this particular convolution layer would correspond to a 7 cross 7. You can verify that on your own. So, what does this provide in terms of computational gain? That is what the the author's claim or the author's claim. That's what it that's the computational gain you get from this, is that if you want to do a succession of 3 cross 3 convolutions, 3 of them, the number of computations involved to produce one element in the output feature map is much lesser when compared to if you just do a 7 cross 7 convolution. Okay. So, this is the, and at the same time you have a larger receptive field on the input. Sometimes it is desirable, in many cases it is desirable to have a larger receptive field, so that you get more of the context in the image into your activation maps. But doing a much larger convolution, using a much larger convolution means that the number of computations increase. So, one advantage of using a succession of 3 by 3 filters, convolutional layers, instead of just using a filter with a larger receptive field, is the savings in the number of parameters. So, for instance, if you had used 7 cross 7 filters on C channels, then the number of parameters would be 49 C squares. On the other hand, if you would use a succession of 3 convolutional layers to get the same receptive field with 3 by 3 filter sizes, then the number of filter sizes would be about 27 C square. Okay. So, this gives rise to this decrease in the number of parameters actually. This might not be very obvious, but you have to do the computation to figure out, because if you have C input channels, then so how do we get this number? If you have C input channels, then the size of each filter would be, if you use a 3 cross 3, the number of elements in which each filter would be 3 cross 3 times C, right. And then if you have C output channels, then we have one more C outside, that is the total number of. And then if you have C output channels, it will be 3 cross 3 times C. Use a 3 cross 3, the number of elements in which each filter would be 3 cross 3 times C, right. And then if you have C output channels, then we have one more C outside, that is the total number of parameters. Okay. Then we have a succession of 3 layers with 3 cross 3 filters. So, if 3 times that. Okay. So, this is how we calculate the number of parameters in when we use a succession of 3. Of course, a similar calculations for 7 cross 7. Okay. So, VGG net by using the succession of convolution layers with very small filter sizes, but of course, the number of parameters is much higher than the AlexNet, but the results were much better. It is about 7% in the top 5, 7% error rate in the top 5, which was in fact that was not the winning, it was not the winning entry, but it won in other categories in the challenges, localization, etc. But the error rate was still pretty good, was around 7%. Okay. So, the winning network was actually the inception network or Google Net from Google. We will see much more about it in the next videos. In this video, we will look at Google Net. The basic building block of this Google Net is the inception module. This is again a 2014 winner of the ImageNet challenge. So, let us look at the basic building block of the inception module. So, for instance, we had for the VGG network that we saw in the previous video, the basic building block was a block of convolutional layers using very small filter sizes. And if you looked at, remember, if you recall AlexNet, now AlexNet had variable filter sizes. So, each first layer had 11 cross 11 filters, and then we had 5 cross 5 filters, and then we had 3 cross 3, and then a fully convolutional network. Okay. So, the inception module incorporates both these concepts, sense that every layer has all possible filter sizes. So, they built a block, a convolution block, which had multiple filter sizes, and they let the network, the backprop, the learning through which the network learns, and let the backprop decide which weights to update based on your objective function. So, let us just quickly look at this inception module. So, if you look, there are two images. So, this here is what the authors of the GoogleNet paper call the naive implementation, and this is the actual implementation that they have followed. So, what is the difference? So, we have an input feature map. Okay, this is the thickness of the feature map right here. Let me use a different color, which will highlight this, right, this good. So, this is the thickness of the feature map, as I have pointed out. Okay, the size, some k feature maps, and we have 1 cross 1, 3 cross 3, 5 cross 5 and 3 cross 3 max pooling also applied to these feature maps. The outputs of each of them are taken and concatenated. So, they are concatenated across that way. Okay. So, again this means that we have to do the convolutions so as to get the same across that way. Okay. So, again this means that we have to do the convolutions so and concatenated. So, they are concatenated across that way. Okay. So, the outputs of each of them are taken and concatenated. So, they are concatenated across that way. Okay. So, again this means that we have to do the convolutions so as to get the same sized feature maps from each of these convolutions. So, they are all 0 padded accordingly and to get the correct size feature maps so that they can all be concatenated. As you will see, doing this has a problem. because the number of computations becomes huge. Okay. So, if you just, so this is the naive implementation. So, but doing it this way, doing the implementing the block, the inception module as they call it this way, has issues in terms of the number of computations involved. Okay, it becomes huge because we have large filter sizes 5 by 5 also in that. Okay, we can also use, I think it is possible to use 7 cross 7 also, but the authors of the Google Net inception module just stop with 5 by 5, probably worked very well for the ImageNet challenge. Okay. So, what is the better implementation? The better implementation is to use 1 cross 1 convolutions to reduce the size of the filter maps. In the sense, when I say size, in this context it is the depth of the feature maps. Okay. So, if you have, so if your input layer has, let us say reduce the size of the filter maps. In the sense, when I say size, in this context it is the depth of. I use 1 cross 1 convolutions to reduce the size of the filter maps. In the sense, when I say size, in this context it is the depth of the feature maps. Okay. So, if you have, so if your input layer has, let us say, if your input layer has 28 cross let us say 192 inputs, okay, so many feature maps. So, in this case let me write it down here, so that this is where we are going to do the 1 cross 1, 192. Okay. So, we would use the 1 cross 1 convolutions to project this number of feature maps to a smaller number, to a smaller volume. So, what I mean by that, we know that smaller number to a smaller volume. So, what I mean by that, we know that, as if you recall, we know that 1 cross 1 feature maps preserve the size of the feature maps, in the sense in plane, the x, y size of the feature maps are preserved, but we can use the 1 cross 1 convolution to reduce the depth of the feature map. So, that is typically precisely what the inception model accomplishes. So, if you have a very large, in the sense of a very wide volume, so very large number of feature maps in the input volume, you would use this 1 cross 1 convolution to bring it down. So, for instance, in this case, let us say we take the 1 cross 1 convolution before the 5 cross 5, we can use the 1 cross 1 convolution to reduce the size of feature maps to 28 cross let us say 16. Okay. And then we can output, let us say, from the 5 cross 5 convolutions, we can output 28 cross 128 feature maps. Okay. Okay. So, just to recall how this is done is by defining 16 1 cross 1 convolutions. Of course, 1 cross 1 convolutions act across the volume, across the feature maps. So, you can also question whether this would lead to loss of information. So, this seems to be a parameter they have tweaked, the number of feature maps here. This has to be done by some kind of cross validation to see which is the most optimal. Okay. So this 1 cross 1 convolutions, prior to doing the larger, this has to be done by, so this seems to be a parameter they have tweaked the number of feature maps here. This has to be done by some kind of cross validation to see which is the most optimal. Okay. So this 1 cross 1 convolutions, prior to doing the larger convolutions with, in the sense larger convolutions in the sense of convolutions with larger filter sizes. So the 1 cross 1 projects the input volume to a smaller dimension, and then subsequently you use 3 cos 3 convolutions to put them back. Okay. So this is what is referred to now as bottleneck layers. Okay. So you shrink the size of the feature map, that way it works. Similarly, for the max pooling also you can do, because max pooling would in most cases preserve the size of the feature maps, the depth of the feature maps, that is, and you can use again 1 cross 1 convolutions to reduce the size. Okay. So this was the two of the big innovations in inception module. So instead of just, so if you saw in VGG that each block they divide the network into blocks. So each block had a succession of convolutions. So in this case, for inception module, it incorporates multiple convolution kernel sizes. Just like in AlexNet we saw that they use 11 cross 11, 5 cross 5, 3 cross 3, but in this case it is 5 cross 5, 3 cross 3, 1 cross 1 and a max pooling layer all in one module. And we also use this bottleneck 1 cross 1 convolutions to project the input volume to a lower dimension in terms of the depth of the volume before we do the 3 cross 3 and the other convolutions with higher filter kernel sizes. So we just look at the network. This had about 22 layers with weights, and so there was an initial set of convolutions and max pooling, okay, which reduced the size of the input to 28 cross 192. So the input as usual was a 224 cross 3. It was followed up by a sequence of convolutions and max pooling, sequence of convolutions 224, 28 and max, and so there was an initial initial set of convolutions and max pooling, okay, which reduced the size of the input to 28 cross 192. So, the input as usual was a 224 cross 3. It was followed up by a sequence of convolutions and max pooling, to get it to 28 cross 192, and then that was used as input to the inception layers, sequence of inception layers followed by max pooling again. A sequence of inception layers followed by max pooling, so on till we have the typical output layer with 1 of 1000 activations. Okay. So, it had so they have labeled the inception modules as 3A, 4B. This was the, if you read the paper, I urge you to go read the paper, where see that they have labeled each of these convolution, the inception modules by 3A, 3B, in this case 4A, 4B, and there is the corresponding table which tells you how the computations are done in that particular module. Okay. So, we will just walk through one inception module, that is 3A, and see how the number of the savings in the number of computations by using a 1x1 bottleneck to reduce the size of the field, reduce the number of feature maps. So, this is a 22 layer network, but then it had very few parameters, about 5 million parameters. Okay. And it won the 2014 ImageNet challenge with a top 5 error rate of about 7%, okay, slightly better than VGG, but with much lesser number of parameters. Okay. So, this was considered this again is one of the networks which have it's very small net, very deep, but in the terms of number of parameters, very less number of parameters. We contrast to, let us say, AlexNet as well as VGG has VGG 16 had 138 million, AlexNet had 60 million parameters, but this only had 5 million parameters. These are weights in the network. Okay. So, we will look at this inception 3A, right here, which takes as input 28 cross 192, and the output is I think 28 to 56. Okay. So, just look at it. So, we reproduced a piece of the table here. I urge you to go back and look at the table. So, this is the output size of the max pooling layer which feeds the as input to the inception. This is the input to the inception module 3A, and this is the output of the inception module 3A. Okay. So, it is the output to the inception module 3A, and this is the output of the inception module 3A. Okay. So, it has 64 1 cross 1 convolutions. So, we saw that if you will go back and we will write it down there just to see, and then it had 96 3 by 3 reduce in that table means the number of 1 cross 1 convolutions done, the 96 feature maps were produced by the 1 cross 1 convolutions prior to doing the 3 cross 3. So, you would produce 128 feature maps with 3 by 3, again 16 1 cross 1 feature maps produced by the 1 cross 1 convolutions following by 32, okay, and then 32 from the max pooling layer, okay. So, the output of the max pooling layer. If we go back, so if you recall some of these numbers, so we would do here, so what it means here is the reduce is basically here. So, prior to 3 cross 3 we would have 96 feature maps here, and prior to 5 cross 5 we will have 16 feature maps there, and then the output of the 1 cross the max pooling would give you we saw 32 feature maps, okay. So, the 3 by 3 produced about 128, okay, and the 5 cross 5 produces 32, okay. 90 other one, that is the one produced by the 1 cross 1 convolution. Recall that, I will once again back here prior to the 3 cross 3 and the 5 cross 5 and the 1 cross 1 convolution following the max pooling, okay. There is nothing before, then there is one plain 1 cross 1 convolution layer, okay. So, which is what we have here from 1 cross 1 cross 3 2, but computations. So, if you look at the following the output of the max pool, which is the input to the inception module, is 28 cross 192. Now, if we directly do 192 3 cross 3 convolution, of course, then the size of the number of parameters in every 3 cross 3 convolution, of course, then the size of number of parameters in every filter is 3 cross 192, and then we produce, let us say 128 feature maps, that is 28 cross 128. Then the number of operations would be about 173 million, okay. Now, if we do let us do the 1 cross 1 projections into a smaller volume. Now, if we do that, then we produce 96 feature maps following the 1 cross 1 convolution, okay, and then we follow it up with the 3 cross 3 convolution to again produce 128. So, we have to do this calculation here for the 1 cross 1 convolution. So, the easiest way to this is again very easy to write it down. I will write this down for the 3 and then the how many computations 3 cross 3 cross 192 sum of products, right. So, 3 cross 3 cross 192, that is pretty much what you see there, okay, that comes to 173 million. You can repeat the calculation here for this one too. So, the output feature map here for the 1 cross 1 convolution is 28 times 96. This is the total number of activations produced. For each activations we have to perform 1 cross 192 multiplications, okay. So, that is what we have here, and then similarly for the 3 cross 3 convolutions we produce 28 cross this plus 28 cross 128, right, and for each one of these activations we have to perform, 3 cross 3 cross 96 multiplication. So, that number is here. So, if we add, you see that there is a reduction in the number of computations that you have just for this one particular feature map, set of feature maps. Okay. So, this was the innovation behind the inception module. So, it does two things. It lets the network decide which feature maps are more relevant based on the back propagation or the optimization. At the same time, as we saw earlier, again even with the VGG net, we saw that using larger receptive fields means that the number of parameters increases and number of computations also reproduced from the paper. 28 cross 28 cross feature map 3 convolutions. The pooled projection layer produces 32 followed by 1 cross 1 convolution. So, that remains fixed. In this case, so they work through the table in the paper and see if the calculations are consistent with the structure that I showed you earlier. Okay. In this video, we will look at ResNet. So, in the previous videos, we have looked at AlexNet, LANet as well as VGG. Now, those layers, for instance, AlexNet had 7 layers, VGG had 16 weight layers, and if you include max pooling, about 3 or 4 max pooling layers in it as well as and if you look at inception at 22 layers. If you look at the progression, so AlexNet was 7, VGG was 16 or 19, inception was 22. They had other versions which are much deeper as well. So, now we come to this part ResNet, where ResNet was different from the networks we have seen so far, is that the number of layers here just increased dramatically. So, these networks had like 30, 50 or up to 152 layers, and there are reports of 1000 layer ResNets being trained. Okay. So, what is the principle, and of course, the ResNet was the winning entry to the image net recognition challenge in 2015, giving rise to a error, top 5 error of less than 4%, about 3.6%, better than humans. Human error rate at top 5 is 5.1% about approximately. So, ResNets were the networks which really tried out with very deep networks in terms of number of layers, and that even really deep as far as 1 150, 152 layers, like I said, about 1000 layers as well for several applications. Now, what is the motivation behind this network in terms of what is the observation that they had before they went to create this model? Okay. So, the paper reports the following. So, they trained deep networks on CIFAR10 data. So, there is a 20 layer network. So, this is the training error for the 20 layer network, and the yellow is the training for the 56 layer network. Okay. Similarly, for the test error, so the test error for the so what is shown here, two plots. So, this plots correspond in training and test error for networks trained with the CFAR 10 database. So, what are shown here are two plots, the training and test error for networks trained with CFAR 10 database. And if you see the one in the yellow layer network, this one corresponds to work. What is the reason behind this? Okay. The reason behind this is that there is a problem with the gradient flow. So, the weights, as you go deeper and deeper, vanishing gradient problem is there. Okay, vanishing or exploding gradient problems is there, and so that is not alleviated, and so it is an optimization problem basically. And so, as you go deeper, optimizing a larger deeper network becomes harder. So, to get over this problem, the ResNet paper introduces something called skip connections. Okay. So, these skip connections are basically identity mapping. So, then since the network just a replication, we will see what that means in the next slides. So, they provide an alternate pathway for the gradients to flow and makes training possible. And for the ImageNet challenge, they managed to train up to 152 layer network. Of course, the number of parameters also sometimes increases with this kind of approach. As you go deeper, you have more layers. So, what is the principle behind which the residual networks work? So, if by construction you can do the following, we know that the shallow network seems to work well. So, we use the weights of the shallow network to construct a much deeper network, and wherever we have gaps we just do identity connections. Okay. We have identity mappings. So, this is just by construction, but For of course, for the real networks are constructed from scratch by backprop, but so the general idea is that if you have a deeper network, its training and testing error should not be higher than that of the shallower network. That is a intuition behind this. So the way they approach this is to have skip layer. So we just, this is illustrated here. So for instance, these are two convolution layers, let us say, okay. They take as input a bunch of feature maps x, okay, and the output is, the output we will denote as h of x, okay. So in addition to the output, what is also done in the RESTnet is that the input is copied here to the output, and the input to this particular convolution layer 1 is copied to the output of the convolution layer 2, okay. So your output, h of x is actually f of x plus x, okay. So how does this help in any way? So instead of learning h of x, you learn the residual. So basically you are trying to learn, okay. So the worst case scenario, if you do not learn, if the weights are not updated at all, it's everything is a very small or 0 value, you will at least learn x, okay. So that is the idea. So just at least, so the gradient flow happens. So that is the, and the residual in this case, that is why it is called learning the residual. The residual in this case, in most cases we would expect it to be small, because the idea is that every layer only slightly perturbs your input. So whatever you have to learn is a very small perturbation of your input, So your residual will be much smaller. Okay. So this is the principle behind doing the skip connections. The authors also show in their paper, and there are presentations available online which show that the gradient update step is additive. So and it is not multiplicative. So the additive gradient step leads to actual updates to your weights, and so it does not, there is no vanishing gradient problem. Okay. That is also explained by the authors. So for the ResNet used in the ImageNet challenge, there is no explanation given in the paper, but typically by skipping, as we saw earlier, skipping 2 layers at a time, the skip connections are 2 layers at a time, you are able to get pretty good results, or very state of the art results, less than 4% error rate on the ImageNet database using the residual networks. So the network itself, using the residual networks, the network itself varied from 30 odd layers to 152 layers. So basically you would alternate this and you would, subsampling was done by either max pooling layer at the beginning or the end, and by just by striding convolutions. And for very deep networks, they also introduced the bottleneck concept in some cases. So you would have a, so in this case you would have, for some of the networks they had bottleneck wherein they had a 1 cross 1, you have a 3 cross 3 and followed by a 1 cross 1. Okay. So that was be replaced by this kind of a bottleneck module for some of the deeper networks, so that the number of computations is kept sustainable. Okay. So and in most modern implementations of all CNNs. Just to clarify, it is actually an addition. So you would take feature maps as input from, as I say in this case, the out heuristic left ResNet seen so far earlier had a sequence of convolution and pooling layers which is still followed today. AlexNet top 5 error rate on ImageNet is 15.3 GG. ResNet had very deep network and for results 30% of convolution. And pooling layers which is still followed today. AlexNet top 5 error rate on ImageNet is 15.3%, VGG 16 had 7.3% layers, so rest 52 to 120 results on the ImageNet challenge. Okay. So we will look at one more network called dense nets in the subsequent video. Welcome back. So last week we were looking at convolutional neural networks, so on and so forth. A head start itself. So we are looking at the script or just the script itself. So let's look at the data first. So you can create one, the object itself. So what it has basically is that it doesn't actually contain the data directly, right? So let's say you have like 10,000 images, right? So you can, and you don't have the hardware to load all of them, so it's not practical to load 10,000 images. You may run out of memory very quickly if you don't have that kind of hardware. So what this image data store does is that it stores the links to the images. So in the sense of the images that you are create a data store object. These are images down here, IMDS, which has all the meta information about the data, right. So what does it do? So you give it the path, and inside you have sub okay. Make sure that you have the data. So the number of images is 10,000, and then you have the data would be training, 20% of the data would be validation, 10% of the data would be testing. To split manipulating the images direct, in case you are going through the piece of code which they have provided. This is so it will tell you, so 6,997 more plus 3, so that's like, you see there are 10% of 10,000 images you arguments, okay. Then you run, I'm trying to make this full screen, it's you them as one, but to do it, so we are using, see what this comes up algorithm. So that now if you are done, then we can close this window, because this just pops up, just tell weights here. This one I'm using this data points that will give, you can create a CNN for this architecture. You just, I'm just remove this, more commonly which has or the folder with part. So make parameter optimization. We'll also look at one application in how CNNs can be used for medical image analysis, And welcome back. In this fully convolutional networks that are used for accomplishing this task. So let's consider this image. However, in many tasks, what is required is actually a pixel wise labeling of the scene. So if you see on the right here, there is the result of a semantic segmentation network shown here. So it has classified each of the pixels into a corresponding category. So for instance, this region here, it's a building. So this region, all the pixels